Hi everyone, my name is Shivaraj Kandhasamy. I'm a research faculty here at IUCAA Pune. Thanks for tuning into the GW at Home 2 series. Today, I'm going to focus on one of the aspects of detector operations, which is the calibration of the detector output into gravitational wave strain. What is calibration? In general, we can define calibration as a process in which we relate a quantity of interest to a measurement standard. So this is a paragraph that you would see under the web page of Bureau of Standards and Measures, International Standards and Measures, where they define this calibration as a two-step process where the first step, using a measurement standard, you establish a relation between the quantity of interest and the standard that we have. And later, using that relation, obtain a measurement result at a later time for that quantity. So for example, a simple case of thermometer calibration, we can use two temperature standards. For example, the cold water, which is ice cold water, which is 0 degrees Celsius, or boiling water at 100 degrees Celsius. So if you put the thermometer in both of them, and mercury will read some values. So you mark them as 0 and 100 degrees. And in between, you may probably make a equal marking. And then you can start using the thermometer to measure temperatures in between. Here, we do assume that the thermal expansion of the mercury is uniform from 0 to 100 degrees Celsius. So there is some assumption goes into in this calibration process, apart from the measurement standard. So what is this means in LIGO? So LIGO, we know that the effect of gravitational waves or any other motions that produces length fluctuations and which in turn converted into light fluctuation at the output of the interferometer. At the output, we have placed a photodetector, and this photodetector sends those light fluctuations and records them. So what we want to do is we want to convert this recorded light fluctuation into gravitational wave strain amplitudes. So this is a process what we call calibration in LIGO. I'm not going to cover how most of these detector operations, which we probably have heard in the previous GW at Home talks. So here I'm going to assume that you have some background about how the detector operates. But maybe something that we have to keep in mind here is that whenever there is a length change in the arms, it produces the power fluctuations and it changes the output at the photodetector. This is all we are going to keep in mind in this talk. So then we want to convert that light fluctuation into calibrated output. So if the interferometer is not controlled, then the calibration process would have been simple. For example, here, this dotted box, let's assume that represents the interferometer. And there is a gravitational waves or a standard reference signal that we have that we can apply on the interferometer. And it produces some output power fluctuation at the photodetector, which is marked as the D error. So since if, for example, if you are applying a known reference signal, and we're looking at the power fluctuation in the output photodetector, then we can calibrate that output photodetector signal in terms of the known differential signal that we have applied. So this establishes a relation between the signal that we have applied and the signal that we see at the photodetector. This forms a relation, and that is the response of the interferometer, which we termed as C. So using this known signal, we can calibrate the response of the interferometer. And then whenever there is a gravitational wave signal comes in, and assuming that the response of the interferometer has not changed, it will produce some output photodetector fluctuations. Since we already calibrated the photodetector fluctuations using a known reference signal, then just looking at the photodetector signal, we would be able to tell what was the strength of the gravitational wave that passed through the instrument. So this is the interferometer. So this process where we take this calculated sensing model, which is C, and we basically apply this for a gravitational signal. We take the signal output and multiply it by 1 over C to get the actual gravitational wave signal. So this process is simple in case if there was no control applied into the interferometer. This is all we have to do. But the problem is that in practical application, like in actual interferometer, we do apply a significant control procedure. The reason that we control the interferometer, like the movement of the arms or the mirrors, is that so here is a picture that's showing the relative position of the mirrors and what is the power buildup in the arms of the interferometer. As you can see, the power buildup is strong dependent on the length of the interferometer arms. And the sensitivity of the interferometer is directly proportional to the power in the arms. So if you want to detect very tiny gravitational wave fluctuations, then we want to have a large amount of power stored in the arms. That requires that we need to keep the length of the arms at some predefined values. However, when we operate the instrument, there are a lot of other things going on around the instrument that can move the mirror and can change the length between the mirrors. So we have to apply some kind of a control process so that the distance between the mirrors kept almost constant. Because of this process, the calibration also gets a little bit complicated. So here now, in the previous slide, we saw that there's only the sensing part, and we can just use the inverse of that sensing response function to calculate the calibrated gravitational strength. But now we also have a control part. So we take the error signal, the photodetector signal, and apply some digital filtering and send it through some actuators so that that actuator can move the mirrors. And they move the mirrors such that they compensate the motion produced by the external disturbance. And this effect is actually frequency dependent. So it is very strong at low frequencies where the instrument is dominated by ground vibrations, and it is not that effective at high frequencies. But still, it has some frequency dependence, so that we need to take care of. So when we do this kind of control of the mirror, then the strength of the gravitational wave that went through the instrument can be obtained using this equation, where this is the actual gravitational wave strength, and this is what we actually, delta L residual is what actually we measure by looking at the photodetector fluctuations. That means the photodetector fluctuation alone cannot tell us what was the gravitational wave signal that passed through the instrument. We also need to look at what is the control signal that we apply to the mirror to compensate the motion of the mirror. So it is like if I have a gravitational wave signal with a strength of 10, some random magnitude, went through the instrument, and it happened to be at some frequency where the activation is applying a control signal, which is like canceling like half of the gravitational wave strength. That means at the photodetector, we will only see a value correspond to a gravitational wave strength of 5. So the other 5 is compensated by this control signal. So if you want to know the actual gravitational wave signal amplitude that went to the instrument, then we need to know what is measured at the photodetector, and also what is the control signal we applied to the mirror. So 5 there and 5 here. So we need to add both of them to get the actual gravitational wave strength. So this reduction in the signal seen at the photodetector fluctuation is generally called closed loop suppression or closed loop suppression. So that quantity is given by this 1 plus ADC, where C is the response function of the sensing function of the interferometer, D is some digital filter that we use to convert the photodetector into some activation signal, and A is the activation that is involved in that path. So generally this ADC, the product is greater than 1, it is 0 or greater than 0. Sorry, it's 1 or greater than 1. So it could also be sometime, sorry, it is 0 or greater than 0, greater than 0. So when it is 0, that means there is no activation. So everything that goes through the instrument will produce the fluctuation at the output. So this part we just saw that to retrieve the actual displacement, we need to look at both the photodetector fluctuation and also the control signal that we are applying. So what is these models of C and A looks like for our detector? So here, this is a graph that's showing how the model of C looks like. So it basically looks like a low-pass filter. That means the interferometer is more sensitive for a low-frequency gravitational signal. As the gravitational signal frequency increases, its sensitivity decreases. So this low-pass filter is defined by two main parameters. One is the gain at the low frequencies, where this curve flattens, and the pole frequency, where this curve turns down. So these are the two quantities that define this low-pass filter. What the calibration process, what we are going to do is we are going to calculate what is this gain and what is this pole frequency for this model of C. What is the model of A looks like? So A is basically it is modeled in terms of the mechanical response of the different stages of the suspension. So here, this is the mirror at the bottom that it actually forms the fabric or cavity. There is a similar structure at the two ends of the arms, and the light is bounced back and forth between the bottom part of this chain. However, we can apply the control signal on other parts, other higher stages also. So generally, we do apply in like at least 3 stages of actuation that we provide, so that we don't have to apply all the control signal at the bottom. We can apply at higher level, and the level of control signal that we apply depends on the stage that we apply. For example, if you want to apply a small control signal, that can be applied at the bottom. But if you want to apply a large control signal, that has to be applied at the upper stages. And the response of these different stages generally goes as like 1 over f square. So bottom stage is 1 over f square, and it increases 1 over f to the power 4 and 1 over f to the power 6. So here is a plot that's showing how it looks like in the model, as well as the measurement. There is a dotted points that you can see on this line. Those are the measurement, and you can see they fit pretty well with the model. So from these measurements, what we are going to get is what is the gain of this line. That means where is this line crosses at frequency 1, and that's all we want to calculate from these measurements. And one thing is that this gain quantity for these 3 stages could vary over time. For example, charging of the optics could change how the control signal is moving the test masses. So that one have to keep in mind. So how do we measure these quantities, the gain in this actuation model, and this pole frequency and gain in the sensing model? So what we do is we apply a known displacement of the mirrors, and we look at and using that known displacement, we can calibrate these model parameters, or at least we can get the values for these model parameters. So here is an example where we have applied a known displacement using a system called photon calibrator that we will see in the later slides. And this is the calibrated HFT in the instrument. Here we already actually calculated the model parameters for A and C, and we put it in those things so that we can get a calibrated HFT. And you can see, wow, since we have applied the correct model parameter for A and C, both the injected values and the calibrated HFT agrees pretty well. So this is an indication that we have calculated these models of C and A very well. So here is as a process. Here is a slide that's showing how this is in actually done. So this is basically showing the model fitting for the sensing function. So in the previous slide, I have shown that C is you have only like 2 quantities, the gain and the pole frequency. But in practice, it's not the case. It also has it is a little bit there's other terms, but these are not as dominant as these first 2 terms. But in practice, we also use these terms to estimate the full model function, model parameters for the C. So this is so here is a model for C, and this is the measurement. And you can see they fit pretty well. And this set of plots, the right-hand side plots, are showing basically the difference between the model and the measurement, and you can see that they are at the level of like a couple of %. So we have a very good model. And here are these plots that show the right-hand side set of plots shows that we basically use so like MCMC, Markov Monte Carlo simulations to get the these parameter values. While doing that, we also explore is there any correlation between different parameter values, and that's what we see from these plots. And if it is like a circular, that means there is no significant correlation between those parameters. But if it has a shape like elliptic or something, so there is some kind of relation between these parameters. That means they are not quite independent. So here, most of them are looks circular, but some of them are like have some shape. But these parameters, they are coupled lightly, but so we do account for that coupling. So once we have these models for A and C and the parameter values for those models, then we can reconstruct the HFT. So here is the error signal that we measure, and control is the activation signal that we send. And since we know A model and C model, using this expression, we can get what is the gravitational wave strain that passed through the instrument. This is the length difference, and the strain is basically length difference divided by the length of the arm. Since the length of the arm is constant, we interchangeably use this length difference and strain in these slides. Also here, I want to note that this activation part is like divided into further 3 quantities. As we saw that the activation, the control is applied in multiple stages. So that means we need to keep track of the gain of each of those stages, which can vary independently. So we model them as independent parameters in this model for A. So how do they affect, or at which frequency region these different models affect the calculation of HFT? So here is a picture that's showing what is the contributions coming from these 3 activation stages, as well as this photodetector signal. You can see that this is the photodetector signal, which is dominant in most of the frequency band of interest. That means we have to use this signal from the photodetector if you want to calculate the HFT. But if you look at the contribution from the activation, so for different stages, it has different contributions. This dotted line is like a 10% level, the contribution that they make. And you can see that the bottom stage contributes from around 10 hertz, like 5 hertz, up to it goes up to 300, 400 hertz. And below and after that, its contribution to the HFT comes down below 10%. So you don't have to worry that much. But if you want to go to uncertainties at the level of 1%, you still have to consider. But this gives how much we have to focus on, like which frequency band we have to focus on working, like identifying problems. For the one stage above, you can see that the contribution goes down even below. That means within about like 200 hertz, the contribution already reaches 10% level. So we don't have to worry about its contribution to HFT above like a few hundred hertz. For example, the topmost stage, here you can see that it crosses the 10% boundary value around like 30 hertz. So above like 30 hertz, it doesn't contribute significantly to the calculation of HFT. So if you are trying to figure out some problems in that particular stage, if it is at high frequency region, we generally don't have to worry about that much, because it doesn't contribute to the uncertainty in the HFT. So now we switch gears. So now in the previous slides, we saw that if we have a reference signal, then we can calibrate our instruments and get a calibrated HFT from the output of the photodetector. But how do we calibrate the displacement, which are like at the level of 10 to the power minus 18 meters? So there are different methods that have been employed in the past and also being used in some of the current detectors. The first one is the free swinging Michelson method, where we use the laser wavelength as the reference. So this is the method that was used in LIGO and also sometimes in the Virgo. Here we basically extrapolate from the laser wavelength reference, which is like 10 to the power minus 6, which is the 1 nanometer laser source that we are using. So we are going from there, it's 1 micrometer laser. So we are going from there to like 10 to the power minus 18 meters. So there's 12 orders of magnitude we have to cover. So this is like a successive step we do this calibration. So whenever we do a calibration that involves multiple stages, the uncertainty keeps on adding in each stage. So this generally ends up being a little bit have a higher uncertainty at the end. But this is an easy thing that to do. So this is probably the first thing that people will try when they are commissioning a new interferometer. Something probably will do even for LIGO-India. The next one is the frequency modulation method. Since we know that the response of the fabric cavity is similar for both the length fluctuation as well as the frequency fluctuation of the laser. Since in the earlier case we were looking at the length fluctuation, but you could also use the frequency fluctuation of the laser to like calibrate this response. And this is what we do in this frequency modulation method. This also requires that you just use one. So in both freezing methods and these frequency modulation methods are applied because you are starting at you basically apply this method when the interferometer is not in its final configuration. When I say final configuration, that means the interferometer is not in a state to absorb gravitational wave signal, but it is an intermediate state. So it basically transferred this calibration from the intermediate to final state in which we absorb the gravitational wave signals. The other one is the Newtonian or gravitational method. This is a new idea that people want to try out, where we basically use a mass distribution and a moving mass distribution. Since we know that there is a Newtonian coupling between any two masses, this moving mass will actually move the one of the masses of the interferometer, and hence it will change the length of the arms. And since we know, since we can calculate what is this force applied by this system that we have been using, and know how much it is producing the motion of the mirror, then we can calibrate the whole interferometer. So there are a lot of uncertainties in this process because we need to know exactly where our mass system that we are using exists in relation to the test mass and how fast is it moving. So all these things we require. So this is this method is at the initial stage, and it seems promising, but it will take some time to come to the precision level of the other methods. The next one is using astrophysical calibration. This is a new idea that people are proposing, where we can actually use the observed gravitational wave signals and general relativity to assess the calibration of the interferometers. So here we are basing our standard is, our reference will be general relativity and the gravitational signal model that we get from general relativity. And assuming that is standard, then from that you can actually try to calibrate the interferometer. So you can get at the level of 15%, 20% using some few signals. But if you have a lot more signals, you can probably do a little bit better, and that's what people are planning to do in the future. The last one is the radiation pressure-based method. Here, basically, we are using an auxiliary laser and shooting at one of the mirror, and using that to calibrate the motion of the mirror and in turn motion length of the arms. This is the method currently used in LIGO detectors and also currently being used at both Kagra and Virgo. So what is the fundamental principle here? Since we know that whenever a light source falls on a mirror or any object, it provides a momentum to the object, and basically translate into force. And the force on that object, in our case the mirror, by a laser with power P, is given by this expression F equal to 2 cos theta P by C, where theta is the angle of incident and C is the velocity of light. This is generally known as the radiation pressure. And here, there are not that many quantities involved in this expression. Theta, we probably could be able to measure, and P is the power of the laser, and C is a constant. Now, if we know the laser power, the P, we can theta and C, we can calculate the force. And if we know the response of the mirror to any force, then we can actually calculate using these two expression F and the response of the mirror to any force. Then we can calculate the displacement produced by a known laser power. So for in a LIGO, the longitudinal response of the test mass can in general be approximated by a free mass above like 20 hertz. So in that case, it basically 1 over m omega square. So basically, so that means the length motion produced by a laser with power p, then basically given by this this expression 2p cos theta c by 1 over m omega square, where m is the mass of the test mass and f is the frequency of the laser fluctuation that we are applying. So here, if you use a 1 watt laser, and assuming that the angle of incidence is 0 and the test mass is 40 kilogram, which is in LIGO case, and if we are applying a power fluctuation at the frequency of 100 hertz, then this produces a length motion of the mirror at the level of 4 into 10 to the power minus 16 meter. This is actually like 100 times larger than what we observed, the maximum that we observed for the first gravitational signal. So this is an ideal system to do the calibration, because one other thing that we want to, it is important in the calibration process is that the signal that we use is at the level of the instrument, also maybe a little bit higher, such that it can produce a significant, a good SNR. So with this system, we can produce a calibrated signal at the level of 100 or 1000 SNR, which is actually ideal for a calibrating instrument. So here is a schematic of showing how this is done. So here you start with the transmitter module. So here we have this auxiliary laser. So this is the one of the test mass. So the main interferometer beam is like coming in this direction and hitting this mirror. So this auxiliary laser is kept on the side, and using like couple of steering mirrors, we send the laser to this interferometer, one of this mirror, and it reflects off that mirror and comes back, and we receive that laser in a receiver model. By looking at the laser power that we sent in and the laser power we received, we can calculate how much laser that impacted the mirror, and if you know the angle of incident, then we can calculate how much this mirror moved. Then that is the length reference that we will be using to calibrate this interferometer. So there is also like actual pictures that showing how they look like in reality, and you can see this this structure is where we have kept the steering mirrors in different parts. So this whole structure is basically to have those steering mirrors in place so that we can inject the laser power into the mirror, and you can see the scale of this this structure. So also here, this picture showing the location of the test mass and also where these transmitter and the receiver modules are. So they are almost like 3-4 meters away from the test mass, because that's where we were able to find a place to put these laser sources. And also this picture shows that we use not only one laser, we basically use 2 laser sources to move the mirror. So in this case, the calibration accuracy is directly dependent on the accuracy of the power measurement. So if we know how much power is actually impinging on the test mass, then we would be able to tell how much the test mass is moving and use that motion to calibrate the output. So if that means we need to know exactly how much power we are sending in. So that boils down to how much would a photodetector or laser source that we are using. So generally what we do is like we don't worry about like the laser source, but we worry about the photodetector that we are using to measure the laser power. So basically we use so these photodetectors, which are also the power sensors. So basically we take them to the, in LIGO case, we take them to NIST, National Institute for Standards and Technology, and ask them to calibrate those photodetectors with the reference that they have. Also, this produces a very good calibration for those photodetector and also establishes a good calibration hierarchy. That means we take our reference to go to a place which actually provides the standard for everything, so that we can get a good calibration for our photodetectors. And this is done periodically so that if there is any problem that happens in between, that we'll be able to identify. So by this process, we were able to get the calibration uncertainty of these photodetectors to the level of 0.5%. So that means this is the minimum that we can achieve with these photodetectors. But in general, what happens is that there are also other uncertainties when we transfer these standards to the interferometer. Then we add up some more uncertainties. Whenever we do extra process that introduces additional uncertainties. So the final uncertainty that we end up with the calibration of the interferometer usually a little bit larger than this 0.5%. So here, this is a pictorial representation of how we actually do this process. So what we call is gold standard. So we have a system. So this is the photodetector, picture of the photodetectors. So we have like a few version of this photodetector. One is called gold standard. Is a reference that we try to keep it carefully in a well-controlled temperature, and that is the photodetector that we take to NIST to calibrate against their standard. Once we calibrate against their standard, then this becomes a good standard for photosensor or power sensor. So we bring this for power sensor, and we have another similar set of power sensors in the lab. So we calibrate those power sensors against this gold standard, and so basically we are transferring the NIST standard through gold standard to these power sensors. Then we take these power sensors to the interferometer site, and we calibrate this receiver model, the photodetector in the receiver model, and thus we are able to say how much power is actually impinging on the mirror and coming back to this receiver model. So since that is the quantity of interest to calculate the length fluctuations, by this way, we are actually calibrating the length fluctuation of the mirror. So as I said, this sensing and actuation function can vary over time. So even if we calculated sensing and actuation at a good this model, we model them very good at one time. They can change over time. So we need to monitor those changes. These changes can happen for various reasons. As I said, charge accumulation in the test mass, or some kind of optical alignment drift in the cavities. So these things can change these model parameters. So we need to continuously monitor them. So to monitor those model parameters, what we do is we inject a very high, like relatively high SNR at the level of 100 calibration lines using the photon calibrators that are continuously injected into the interferometer. So that means whenever we look at the output of the interferometer, we will always see these lines present in there. Since we know how much we are actually moving the mirrors at those frequencies, then we can calibrate the response of the interferometers continuously, at least at those frequencies. Then using the initial models, then we extrapolate the sensing and actuation model at any time. So here is an expression in the previous case. The strain of the gravitational signal is given by 1/c model and R mirror. But here now we have an additional factor, which is a time-dependent quantity. This is monitored by looking at these calibration line heights that is continuously running in the interferometer. And similarly, you have a time-dependent factor for actuation model. In practice, we have like three such factors for the 3 stages. So here is a picture that's showing how this time-dependent factor changes over time. So this is during the O1 for hand detector. This is for the gain factor. Basically, this is the gain factor for the bottommost stage, which is the test mass. And you can see that this is not constant. This is changing over time, and it is actually changing at the level of like a few percent. This is in via x-axis in terms of days. You can see that for 1 month, it changes by like 3%. This changes due to, as I mentioned, charge accumulating at the test mass. So this happens, and if we don't do anything in 3 months time scale, we will have a accumulated uncertainty of like 10%. For the other stages, we see that it's not, they are relatively stable. The changes are not that much. For the gain for the sensing function, it depends on the state of the interferometer. It could be fluctuating, but in this case, it was relatively stable, at least during O1. This is the similar time-dependent factors for Livingston detector, and we see similar change in the bottom stage actuation strength, and there is not significant change in the other quantities, except here you can see that the sensing gain was changing slowly over time. That means that there was some kind of loss in the optical power loss in the interferometer that was reducing the sensitivity of the instrument. So if you look at the spectra calibration, the LIGO detector spectra, and you can see that there are many lines, and you would all be, if you know the frequencies of the calibration, you'll be able to see. So here I have pointed out the calibration lines that is used in O1. One that we use like 3 lines in each interferometer. Apart from these lines, there are also other lines that exist. They're coming from the power lines, and also the different modes of Boolean modes of the test mass wires, and also even the test mass body mode itself. Basically, we monitor the height of these lines, see if there are any changes in the model parameters of those C and A. So once we have these models of A and C, then we can produce the calibrated gravitational wave strain output. This is done in 2 steps or 2 ways. One is online calibration, where we use these models to compute a strain output, which happens like within 5-second time scale, and it is into various computing clusters. This is used for like initial analysis, which is needed for like rapidly following up of events with other observatories, like electromagnetic observatories. But then we also do an offline calibration, which is done once the run is finished. Here, what we do is we go back and see if there was any error in the online calibration, or if there was any data dropout that we missed. So we go through all those process, and we fix all those things. So generally, this offline calibration has less uncertainty than the online calibration. And this is what we use for the parameter estimations when we publish the final papers. So this is a uncertainty plot showing what we had for during O2. So here, Hanford, Livingston, and Virgo. This is uncertainty plot for 3 detectors. And you can see at some frequency band, both Hanford and Livingston has an uncertainty at the level of like 1% or 2%. And at the time, Virgo reported a flat uncertainty. They being conservative, they provided a flat uncertainty of like 5%. So I said this is achieved for the offline calibration. If you look at the similar plot for online calibration, which would little bit larger than this, maybe like 1 or 2% larger than this. Not too much, but 1 or 2%. But if you are trying to calculate something to the precision of like 1% or 2%, these differences matters. So here, this question probably should have asked at the beginning, but why do we need such a precise calibration, put so much effort? Because if you want to do cosmology, astrophysics at some level, like calculating Hubble parameters or even CBC rates, we actually require a very good calibration. Right now, we are generally limited by the observations. So we don't have a very not that many signals with high SNRs. So once we started to see very high SNR events, then the calibration uncertainty will become very important. So at this point, we are still limited by the systematics in the analysis, but we hope that as we move towards the next generation of detectors, we will be limited by the calibration. That means we need to improve the current calibration precision. I said this, if you want to do good estimation of H0, Hubble parameters and compare it with the other measurements, for example, CMB, then we probably have to have a very good calibration. And also having a good calibration is important if you want to look for deviations from general relativity in the signals. Since we are looking for since we know that general relativity, at least on a bigger level, holds true, that means if there are changes, if there are deviations, that should exist at a very small level. So if you want to detect the things at that small level, then we need to be we need to have a good calibration. That means we know almost all the systematics in the data, so that whatever systematic that we see then would corresponds to some deviation from general relativity. So there are challenges even in this current PCAL method. So in the next 2 slides, I'm going to point out a couple of those challenges. One is this the rotation of the test mass. So as I said in the earlier slide, we apply 2 beams, not 1 beam configuration, to move the mirror. The reason that we apply 2 beam is that the interferometer beam is at the center of the mirror. So we don't want to put any other external beam at the location where the main interferometer beam is, because these even though the small auxiliaries laser, they can actually deform the mirror, which can be sensed by the main beam as the motion of the mirror. So it cannot differentiate between the actual motion or some kind of deformation of the mirror. Both of them would look similar for the main interferometer beam. So to avoid that, we actually apply these 2 beams far away from the main interferometer beam. Since we are applying 2 beams, and if the 2 beams are not balanced properly, both in location and in power, then it can produce a rotation in the test mass, which will actually mislead our calibration process. So how much that correction is given in this red quantity, 1 plus m over I a dot b. So it depends on what is the imbalance that we have in the beams, and also mass and moment of inertia of the test mass. So the one way that we can actually monitor or test this is to look at the position of these mirrors. So we have so here at the bottom picture, you can see we generally, whenever we do when we install this photon calibrated system, we actually use this setup to position the mirrors exactly at the point that we want. And we also have placed cameras that actually look at these the test mass and see where the beams are, so that we can continuously monitor the location of the beams. And if there was any change in the beam location, either we can account for that in our calibration process, or we can go in and correct that in place. The other challenge is coming from the deformation of the test mass. So even though the test mass, the optics looks like a rigid body, it has some natural frequencies that close to those natural frequencies, it will be like a very fluid, it will bend, and it will do all kind of deformations. So whenever, if you're applying, for example, if you want to calibrate this test mass at 5 kilohertz, then we have to apply the photon calibrated beam, the power fluctuation at the 5 kilohertz frequency. Since this will be close to the one of the modes of the test mass, then the test mass will start to deform. So that will then mislead our calculations of how much the test mass is moving. So that will affect the calibration process. So this kind of the bulk deformations is one of the issues if we want to calibrate at high frequencies. And we probably want to calibrate at high frequencies if we want to calibrate the gravitational strain at these frequencies, which is crucial for studying, for example, neutron star matter, neutron star equation of state. If you want to study or any matter-related things that we want to study, then we probably have to look at the strain at high frequencies. So then we have to see how we can deal with these deformations and how we can account for. Generally, it is a little bit hard to model, so we have to invest a little bit more time if you want to calibrate at these frequencies using photon calibrator. Right now in LIGO, we go from 20 hertz to 1,200, 1,300 hertz. and we are at high frequencies. We assume that this calibration can be extrapolated. Even we don't. So here, this is the uncertainty level. So we basically extrapolate from like 1,200 to 3,000 hertz. We extrapolate, assuming that the same calibration exists above that frequency. But if you want to actually see by applying a photon calibrated beam, that we need to worry about these deformations. And also this picture shows that not only like this is important at close to the body modes of these objects, even like a little bit further away. For example, here for example, the first body mode of our test mass is around 6 kilohertz, where the curve shoots up at the top. But even before that, for example, 4 kilohertz or 5 kilohertz or 4 kilohertz, the deviation from 1 could be like at the 10% level. So if you are trying to calibrate something at the 1% level, then we have to worry about these variations, even a little bit further away from the actual modes of the system. So now we see how we calibrate like a different interferometers. So until now we looked at how we calibrate one interferometer, but generally whenever we do data analysis, we basically look at the signal from many different interferometers. So we need to have a common standard among these many different interferometers. So one of the things that people are talking about is like using one gold standard that is calibrated in NIST or any other national standard, then using that gold standard, calibrate the local standard at different sites. Currently, this is being implemented at LIGO-Hanford, LIGO-Livingston, and Kagra also wanted to use the same gold standard. I think Virgo also tried. When LIGO-India comes up, maybe we will also do something similar. So this is an uncertainty budget which defines what are the uncertainties in using PCAL as a calibrating system. So the dominant one is the actual power calibration done by the NIST, which is 0.3%. So that all of these things adds up to like 0.4% total calibration error. So in the previous slide, I mentioned it is 0.5%. So it is a little bit less during this new observing run 03 because we identified some of the systematics. So this is one slide which compares. So until this point, we say that we take our standard to the NIST, one of the national standards in the US, and calibrate the power sensors. But there was a study where people took a power sensor to different national standards labs. And they found that there are some differences between these measurements at different labs. So this may be some kind of systematic in the system, or maybe something that they need to follow up. So after this study, then people were started looking at why we have. You can see the discrepancies at the level of like 2%. But if you want to calibrate something at the level of 1%, then we need to understand why different national standards have different, like national labs have different. Different national labs calibrate these sensors differently. So they are trying to understand these differences. I think some of these differences are like started out now, but still, but this is something that that started this regular comparison of standards between different national labs. So maybe when LIGO-India, we probably can use something similar with NPL, National Physical Laboratory here. So conclusion. So currently the radiation pressure based photon calibrators were successfully used in advanced LIGO to calibrate their data. Currently the calibration uncertainties are at the level of a few percent. This is mostly limited by the uncertainties in the model function and the sensing functions. And also it's not currently limiting the signs that we get out of the gravitational wave signals. But in the future, when you want to extract astrophysical information such as Hubble constant to good precision, then we need to reduce this calibration uncertainties to the level of 1% or below. And this requires a little bit work on the current setups, the photon calibrator, or new methods that are being developed. Thank you. That's all I wanted to cover during this talk. And I am done. So I see there are a few questions that are already listed here. Gopi Patil is asking, what if we don't have a reference signal for calibrating? I think this is pretty important for any calibration process. We need to have some kind of reference signal or some kind of standard so that we can calibrate against. So that is required, but the kind of reference, but there are many different references that are available. So we don't have to like just use photon calibrator or like a laser wavelength reference. We could go with something new, but at the end we need to have some kind of reference. Okay. Next one, Shodip is asking, do we have any plan to use single photon source and single photon detector? At this point, no, because if you look at so what we want to see is that how much the test mass moves when we apply a laser source. And it turns out that even if you apply like a microwatt laser, the amount of motion that we can produce is at the level of 10 to the power minus 17, which is like only 10 times larger than what we want. So for one photon source, we probably won't be able to see with our current detector technology that the test mass actually move. So in that way, we probably won't be able to do. So we want to see the test mass is moved at some level. Currently, we cannot see the motion produced by a single photon. Okay, Vaibhav, how is the reference signal injected while calibrating? So when I say reference signal, it's basically like known displacement produced by the photon calibrator. Since we know how much power we are applying on the mirror, and from that we know how much the mirror will move. That is our reference signal. And that motion corresponds to some amount of fluctuations of the photodetector that we see. That's how we calibrate our photodetector signal at the output of the interferometer. Okay, Aditya Mishra is asking, what are the astrophysical phenomena can be used for calibration? I think most of the gravitational signal in principle can be used, but that assumes that we believe in the GR and the waveform produced from these GR models. If we assume that, then we can calibrate the instrument. But in general, what we are interested in is looking at the signal, and we want to get some information about the sources. And if we are looking for something like beyond GR, then we cannot use this process. So Aditya Mishra is again asking, the calibration done at really low temperature, that is set up including the photodetector and mirror operated at very low temperature when being calibrated. Now everything is done at room temperature. The current LIGO detector operates at room temperature. The CAGRA detector is a cryogenic detector, but the sending in the laser could be done from the room temperatures. Outside, where the laser sits, it could be at room temperature, and the actual detector, the mirror, could be kept at low temperature. That's what's happening at the CAGRA. But for LIGO, everything is at room temperature. And that is not something that is important in this process, at least at this point. Next question is, does the movement of the sun and moon changes the instrument response? In principle, anything that moves can produce a quadrupole change, can produce gravitational wave and affect our instrument. And sun and moon changes also produces gravitational waves, but the calculated values suggest that they are too small to be detected by our instrument. That means we won't be able to see their effect on our instrument, because we will be dominated by other noise sources in the instrument. So once if we can reduce this, so I think the level is like at least 10 order of magnitude, I think 38 So currently we are at the level of 10 to the minus 18. So we have to go like 20 orders of magnitude to see that signals. Is the detector constantly being calibrated in online mode? If yes, then does the calibration signal interfere with the gravitational signal? So as I mentioned, we do inject 3 calibration lines in the instrument, so that they constantly being run. So that means at those frequencies, if there is a gravitational signal exists, we won't be able to detect them because that is dominant. At those frequencies, it is dominated by the reference signal or the calibrated signal. So that is the downside of using something that is running all the time. So we won't be able to detect signal at that frequency. But all the signals that we are looking at are like a broadband. So removing a small narrow frequency band is not a big problem. But if you are looking for like a pulsar at that particular frequency, which only emits a narrow frequency, then that's a little bit problem. So that's why currently the calibration lines are moved to very low frequency, like what we call out of band. So currently the band of interest in LIGO, or at least that we produce calibrated data, is from 20 hertz to around like a 3-4 kilohertz. So currently the calibration line are kept below 20 hertz, around 16 hertz, so that it doesn't contaminate the band of interest. Okay, Swarang Saraf is asking, how do Newtonian defects affects accuracy? I'm not quite sure what the question is. What kind of Newtonian defects that you are asking? I think those are the questions that I'm seeing. Okay, I think it looks like there are no other. Okay, well, Vaibhav is asking, how can one pursue a career with LIGO-India in this field? Maybe you might have heard from the previous few talks, at least some of the opportunities that is available as part of LIGO-India, and also in general LIGO. There are like opportunities for at different level of studies, undergraduates, graduates, and PhDs. Right now, our focus here in IUCAA is for training undergraduate students and probably master students. And we are also hoping that we will have some PhD level labs here, and also like other places in the country working in the LIGO specific field. So if you're interested in some of these projects, you can look at the IUCAA webpage. There is a research opportunity subpage in there. You can go to gw.iucaa.in, and there is a research opportunities page where we have listed some of the opportunities for undergraduate and graduate students. You can go from there. You can also contact the LIGO-India faculties in different institutions if you are further interested in continuing career. Okay, I think it seems there are no other. Okay. Okay, so I think there are no other questions. Okay, thanks for tuning in. And if you have any other further questions, you are feel free to email to EPO and or us or other people who are working in LIGO-India. And one thing, so before I finish, I want to mention that next talk will be on 3rd August, Monday. It will be by Professor Unikrishnan from TIFR Mumbai. The talk is titled Surfing in Physics with the Waves of Gravity and Electromagnetism. Seems an interesting topic. And he's also giving another talk on 7th August, Friday, titled Gravity's Time in Physics, Life and GPS. So these are he's an experimentalist. I think you will hear his take on this LIGO-India and also gravitational waves from these talks. Thanks, everyone.